agenda for today. We will talk about GPU computing in a general sense. We will review the GPU computing APIs that are currently available. We will then look at general GPU computing concepts. Then we will see how these concepts are mapped to the Wolfram language. And finally, we will explore the two available APIs in Mathematica. One is called OpenCL and the other one is called CUDA. If you talk about GPU computation, we usually now mean general purpose computing on graphics processing units, which is abbreviated as GPGPU. GPGPU means the use of a GPU. That means a graphics processing unit to handle computations traditionally handled by the CPU, which is the central processing unit. If you're like me, it always pays off to really look at the hardware things we are talking about. So, for example, here on the slide, you see a modern NVIDIA card, which you might find when you open your desktop computer. And this NVIDIA card is connected to your system using the PCI Express bus. And it usually is quite an impressive piece of hardware. On the other side, we have the CPU, which is just a small device, which is usually located on your motherboard, and which contains the CPU. And if it's a modern CPU, it may also contain an integrated GPU. What is the difference between these different technologies, CPUs, GPUs, and system on a chips? A CPU is the general purpose instruction unit in your machine. It executes instructions which cover basic arithmetic, logic, controlling, and input and output. As the CPU typically have a few multi-threaded cores, like for example, the machine I'm currently using has 4 cores, and desktop machines have now up to 16 cores usually. The CPUs have cache built in, and the RAM is usually external. GPUs, on the other hand, became popular at the turn of the century, and they were designed to rapidly manipulate memory to accelerate the building of graphics in a buffer for output displays. It means the rendering of some graphics is handled on the GPU, and then the buffer is output to the buffer is output to an output display. Instructions cover only numeric arithmetic. That means, for example, on the GPU, usually, for example, string processing is not doable. GPUs are massively multi-threaded many-core chips. That means compared to a GPU usually has hundreds of cores compared to at least compared to the few cores that are available on the CPU. But these cores are not as general purpose as they are on the CPU. GPUs also have a cache memory built in, and this cache memory is dedicated for doing graphics operations. Recently, another type of chip has become popular. This chip is called system on a chip, and this system on a chip is a chip where the GPU and other components are integrated with the CPU. For example, these modern Intel Core processors that are now in all portable machines usually have a so-called integrated GPU, but the RAM is still external. Recently, Apple has introduced a new processor which also has now the RAM integrated into the chip, so that we are seeing a convergence of all these different technologies on our system on a chip. And I'm sure that this is the future which we'll see in the coming decade. More or less all the computing devices will be offered as systems on a chip. What are the main GPU vendors? We have NVIDIA. NVIDIA was one of the pioneers of GPUs. They have three types of graphical processing units. They have the desktop GPUs, which are usually the GeForce series. They have mobile GPUs, which is the GeForce series for mobile. And they have high-performance workstation, high-performance computing GPUs, like, for example, the NVIDIA Quadra, Tesla, Kepler, Maxwell, and Pascal series, which are much more expensive than the mobile or desktop GPUs. And this is when you're serious about GPU computing, this is one of the cards that you need. Then we have AMD. AMD it's the main competitor of NVIDIA, and they also offer desktop GPUs, mobile GPUs, and workstation GPUs, which usually are available under the name Radeon. And the high-performance GPUs are called FirePro or FirePro Stream. Another important vendor is Intel. Intel, of course, doing CPUs, but most of the CPUs now have an integrated GPU, and here they also have consumer GPUs and Pro GPUs, which is the Iris Plus series or the Iris Pro series. What I also learned in myself in preparing this talk is that Intel also offers standalone GPUs, which is, for example, the GPU XE series. If I look, for example, if I bring up the about dialog about the machine that I use here, you see that, for example, my machine is equipped with an Intel Core i7 processor, and it has an Intel Iris Plus graphics as integrated GPU. And the GPU memory is 1.5 gigabyte, while the main machine has a main memory of 32 gigabytes. This is typical for modern notebooks. On the software side of things, we need software components which let us talk to the GPU hardware. And the different GPU vendors have devised so-called software APIs, that means application programming interface, which lets you interface with the device on your system. There we have two different APIs which have become popular. The first one is called CUDA, which stands for Compute Unified Device Architecture, and it was created by NVIDIA. It was the first available API for doing GPU computation. It is still only supported by NVIDIA GPUs, and it lets you run code on an NVIDIA GPU. This is the most advanced API that we have nowadays, and it's still it's the most efficient API that is currently available for doing GPU programming. On the other side, we have an APU which is called OpenCL. OpenCL stands for Open Computing Language. OpenCL is a framework for writing programs that execute across heterogeneous platforms consisting of CPUs and GPUs. It was initially created by Apple, but Apple then gave it away without profit to the technology consortium called Kronos Group. Kronos Group is also the responsible for OpenGL. And they now maintain the OpenCL technology as an open standard. And the consortium is made up by companies like Apple, AMD, Intel, NVIDIA, and others. And the main advantage that OpenCL has, of course, over CUDA, that it's available for all different types of GPU cards, and it also lets you run code on CPUs. This is really a major issue, because if you do any kind of serious GPU programming, you usually have to do a CPU implementation in order to verify the results that you get from a GPU. And with OpenCL, this is trivial to do, because you can run the exact same code that you run on your GPU also on your CPU. Another API that I want to mention is called Metal. Metal is an API that Apple has established as the successor of OpenCL. Actually, Apple has deprecated the use of OpenCL in newer machines, and the new machine, the new API called Metal, is now intended to replace both OpenCL and OpenGL. But at the time being, the old version of OpenCL is still supported by these new ARM-based Apple Silicon Macs. And of course, the Intel Macs also can run OpenCL code. Unluckily, Metal is not currently supported by Mathematica, and it will be interesting to see how Wolfram will change Mathematica once Apple completely drops support for OpenCL. How can we exploit? Why would we want to use the GPU at all? GPU lets us exploit parallelism that is implicit in the things we do with computers. Oftentimes, when we run programs, we do the same things many times. For example, when you use Mathematica, you usually do the same computation with many different inputs. Or when you do a Mathematica with Mathematica and Monte Carlo simulation, you run the exact same computation on each part of this Monte Carlo simulation. Or if you're rendering frames of an animation, then each frame of this animation is rendered in the same way. That means the same computation is performed. This gives us a huge opportunity to exploit data parallelism. That means we can, since the computation is the same every time, we can run these things in parallel. And many operations of the form where we have a function which some long lists of arguments can be parallelized using this method. We can divide, for example, the long list in a set of pieces, as many pieces as there are processors. Then we compute these individual pieces in parallel, and then we combine the results using a combination function. And this is where the GPU comes in. The GPU lets you efficiently optimize the computation of these individual pieces, and then you can receive the results from the GPU and do the combination of the results in another GPU computation step, or if it's a very complex computation, you can do it on the CPU then. But the real speed up comes from running the individual computations on the GPUs. What are the main concepts in GPU computation? There's the so-called notion of a host and a compute device. We have a host, which is usually the machine that you're using, and on this machine you have a set of compute devices, and these set of compute devices contain compute units which contain processing elements which let you run code in parallel. And usually on a normal machine like this one here, you have two compute devices associated to the host. First one is the CPU and the second one is the GPU. But on a desktop machine, it's completely normal to have, for example, 3 or more graphic cards installed on the desktop machine. When we are doing GPU programming, we have to completely change our mental model about programming. Usually, when we do CPU programming, we are used to we know exactly we write some code. This code is then translated to machine code, and this machine code is made up of instructions. And we know that the CPU simply goes through these instructions one at a time, and then runs the instruction. The instruction may do some computation, it may fetch some memory, or they may do some control flow. But essentially, it's a very simple concept which has been done like that for a century, for many decades. Of course, the CPU may apply some clever tricks to exploit parallelism or the modern CPUs also use a pipeline in order to use instruction level parallelism. But essentially, the CPU processes instructions one at a time. With the GPU, we have to think in different terms. With the GPU, we move work groups which consist of work group items through the GPU, and the GPU processes these work groups in batches. That means, for example, if we have four work groups, the GPU will look at each of these work group, then run the computation that described in this work group, and then move on to the next work group. What is a work group in detail? The GPU has the following execution models. A work group can be an n-dimensional thing. That means it can be a one-dimensional thing, it can be a two-dimensional thing, or a three-dimensional thing. For example, here we have a two-dimensional work group, and this work group consists of work items, and all these different work items, which are shown in yellow here, are executed at the same time in parallel by the GPU. And all the different work groups make up the whole set of the computation, which is called ND range. ND range stands for n-dimensional range, and depending on the size of the ND range, the amount of work groups is determined. On the terminology that is shown here is the OpenCL world terminology. On the CUDA API, we use different terms. Instead of work item, what we call a work item in the OpenCL world is called thread in the CUDA world. A work group is called a block in the CUDA world, and the ND range is called the grid. Unluckily, the terminologies are different, and if you read information on the web, you will still find both terms used very frequently. How does the GPU? How is the GPU able to scale our computation given these work groups and blocks as they are named in CUDA? Let's, for example, let's say we have multi-threaded programs which consist of 8 blocks, and these 8 blocks are then executed, for example, on a GPU with 2 compute units or SMs, as they are called in the CUDA world. If we have 2 compute units built into our GPU, it's able to process 2 blocks or work groups at the same time. It means it goes through the whole computation program in 4 sequential steps. If we now move to a more powerful GPU, which has 4 streaming multiprocessors or compute units, the GPU can now simply execute 4 blocks at the same time. That means our processing time is reduced by 50% because the amount of streaming multiprocessors has increased by 2. And so this is where by what you experience when moving from a low performance GPU to a high performance GPU, you usually can gain speed because these more expensive cards have much more compute units, which lets you run more computations in parallel. How do we get the actual code to the GPU? The GPU, of course, needs to run some code which does the computation, and this code is called kernel. Unluckily, if you, as Mathematica users, we know the term kernel is also used for the Mathematica kernel, but here the term kernel means something completely different. A kernel roughly corresponds to the inner loops when implementing algorithms in classic CPU-based languages. Like, for example, typically kernel code would simply add a few numbers or perform a computation on some data and write the results to an output array. And how is the process? How does the process of running kernel code work? We usually have to provide the OpenCL code in source code form at runtime in a string or in a file. We then call an API function. This API function will then compile this code to native code, which depends on the actual GPU that we use. The GPU code will be loaded onto the GPU, and then the kernel code can be executed. Depending on the different GPU device we have, like for example a CPU, a GPU, a DSP, a digital system processor, or an FPGA. This is all handled by the API, and we only have to provide the source code of the kernel. Of course, the code has to access some parameters and memory. And how do we do that? That's what we see in the memory model. Unlike, for example, on the CPU side of things, handling the memory is very trivial. We have main memory, we have cache memory on the chip, we have registers. And usually this is all completely transparent. That means the memory is simply a flat array, and the hardware and the operating system takes care of moving the needed data to the processor. On the GPU side of things are not so simple. That means as a programmer, we are completely exposed to the different types of memory that are available on the GPU or on a compute device. Here, the first type of memory we have is the so-called global or constant memory. This is the memory as it is advertised on the box of the GPU card. For example, on the machine that I'm currently using, it's 1.5 gigabytes. And then we have so-called local memory, which is shared by all different compute units when they work on a certain compute work group. And then we have private memory, which is completely private to a single work item, where the kernel code can use local variables and registers. And interestingly, this compute unit memory, this local memory here, is only a few kilobytes, usually 64 kilobytes or even less. And the main advantage over the global memory is that it's much faster to access local memory from compute units than it is to access the global memory. That means if you want to really optimize your GPU programs, you have to take care of moving your data from global memory to local memory in your kernel code. But this is not necessary if you just want if you're just developing simple programs, as we do in this presentation. How does the workflow from a programmer's worker point of view work? When we want to run code on the GPU, we first have to allocate GPU memory. We have to then copy CPU memory, which contains our computation input to the GPU. Then we have to configure the threads that are going to run on GPU. We have to launch these threads. Then we have to compile the CUDA code or OpenCL code, kernel code. This is then run on the GPU. Then we have to synchronize all the different threads so that they wait until they complete all the computations. We have to copy the memory back to the CPU, and then we free the GPU memory. This is a very complex process. And for example, I have printed here how it looks when you use the OpenCL API here, which is included here. You see that all this is different. This is really boilerplate code, which is very cumbersome to write, and which uses a low-level C++ API, and it's not really fun to use these kind of computations. And here Mathematica comes in. When we use Mathematica, Mathematica frees us from all these different tasks. Mathematica completely handles the GPU memory. From us, it handles copying the memory to the GPU. It handles configuring the threads. It handles launching the threads. The only thing that we still have to do is run the kernel code. This is something that Mathematica does not do for us, and also Mathematica is not able to run arbitrary Mathematica code on the GPU. We still have to write the kernel code in this low-level C dialect that is used by OpenCL and CUDA. Once the computation is done, Mathematica takes care of retrieving the results from the GPU and copying the memory back to our Mathematica session. So Mathematica supports both APIs, which are popular, both OpenCL and CUDALink. We have two packages which comprise these APIs. The first one is called CUDALink. The other one is called OpenCL-link. Both APIs or both packages have low-level functions and high-level functions. The low-level functions cover handling the GPU memory. They cover compiling GPU kernel code, and they enable the programmer to run GPU kernels on the GPU. Then we also have high-level functions which completely which mimic existing high-level functions in Mathematica. These high-level functions simply execute code on the GPU, but other than that, they are working the same way as built-in functions. And these functions, these high-level functions, cover areas like linear algebra, image processing, Fourier transformations, quantitative finance, and even a neural network training. Let's just have a look at all the available functions here in CUDALink and in OpenCL-link. And let's just blow this up a little bit. And you see, for example, unluckily, the low-level functions are basically the same for both packages, but the high-level functions, like for example image processing and signal processing, are only available on CUDA at the time being. For example, for CUDALink, we have functions as CUDA image, Wolf, image revive, and all these things. Whereas on the OpenCL side of things, we only have high-level functions for rendering fractals in 3D, for example. All the other things are really low-level functions. The first thing that you usually do when you use GPU code, when you want to use the GPU in Mathematica, is inspect the hardware that is available on your system. And there we have we can test out for if our system supports OpenCL. Since this is a Mac machine which supports OpenCL, it returns true. And we can then obtain information about the OpenCL platforms on devices on the system using the function OpenCL information. This returns all properties of the hardware. And since this is not very clear, let's just wrap this information in a data set so we can easily browse through all the available information. We see here that the device here is an Apple-provided device, and it has two different devices. The first one is a CPU device, and the CPU device is the Intel Core processor. It has 8 cores, and if we scroll down on the list of properties, for example, we see here that it has a maximum memory of 32 gigabytes here. Let's just go back here and inspect the other device. This is the integrated Intel Iris graphics card, which supports OpenCL 1.2, and it has 64 cores compared to the 8 cores of the CPU. And it has, for example, the global memory size is 1.5 gigabytes, which corresponds to what we see here in the about dialog about this Intel Iris machine here. On the CUDA side of things, we can simply load CUDALink, and here we can test if the system supports CUDA. Unluckily, Macs no longer have NVIDIA cards built in, and even NVIDIA does not provide the SDK for NVIDIA cards since a few years now. So that means I have pre-evaluated this CUDA information function here on the desktop machine in order to view the output of this function. For example, on the desktop machine at my office, I have built in an NVIDIA, the GeForce GTX 1050 card, and this card has, for example, a core count of 640, which is quite impressive compared to this integrated GPU cards. And it has, for example, a total memory of 2 gigabytes. One important information that we can derive from this OpenCL function information is the maximum work group size and the maximum work item size. Let's just evaluate these functions here. Here we see, for example, that the CPU device installed on my machine has a maximum work group size of 10,024, and the maximum work item sizes of 10,024 times 1 times 1. The maximum work group size determines the maximal amount of a work group, and the product of these different dimensions here must not exceed the maximum work group item size. On the GPU side of things, we have on this Intel Iris that is built in has a maximal work group size of 256, but the actual dimensions are also delimited by 256 in each dimension. And that means we can, if we want to plot the sizes of our work items, we can, for example, if we're working with one dimension, we can blow up the width until we reach 265. But if we want to also add a second dimension, we have to reduce our width so that we can add an additional height to our system. And if we blow up the height here, for example, we must never exceed the maximum size of 256 threads, because the hardware is not capable of handling more than that amount of threads. If we, on the other hand, we want to go into 3 dimensions with our work group, I even have to reduce the both dimensions, and I can then, for example, add in a third dimension to my work group. And this is very important. That means you have to plan ahead the work group size that you are going to use, because the whole work group size must not exceed the amount you see here. On the CPU side of things, for example, there is even this is even more restricted. We can't even work with 2 or 3 dimensions. We have to map all the problem space to 1 dimensions if we want to run the OpenCL code on the CPU device. Let's now look at a very simple OpenCL example, which runs, how can we run this code with Mathematica? Here we have to provide the source code in string form, and we have this string form uses the C dialect, which is defined by OpenCL. We can then we will look at the details of this kernel code on the next slide. Let's just now look how we can run this code with Mathematica. We first have to load the function where we pass the source code to OpenCL function load. Then we pass the name of the function, which corresponds to the kernel name. And here we describe the interface of the function, which corresponds to the parameters we see here. And then the last argument is the work group, the work group dimensions that we want to use. That means we work with 2 dimensions, where one dimension has a work group item size of 16, and the second dimension is set to 1. We now load the function on the CPU. That means by this function here actually goes through the whole process of compiling the function for the GPU, and then it returns a function which can be used as a built-in Mathematica functions, similar to how we use, for example, pure function in Mathematica. We can run the compiled OpenCL code. We create some input range of 265 numbers, and then we simply call the code here. And as you see here, it simply has I've created a range from 1 to 265. Then I've converted it to floating point numbers, and then I've called the OpenCL function, which simply has added the constant 2 to each of the input vectors. And as you see here, the interesting thing here also is that how do we pass data and receive data from the OpenCL function? This is determined by the third argument to which we have to specify for our parameter, which means simply this parameter to our function will be copied to the GPU upon before the kernel code is launched, and then it will once the computation is run, it will retrieve back the generated code, and it will then be returned as a Mathematica array into our Mathematica session. Let's now have a detailed look at the kernel code, what these different things all mean here. Here in this kernel code, you see we have a kernel annotation which tells the compiler that this function will be run on the GPU and is callable from the CPU. We have the return type is void, which in C terms means that the function does not return a value, because a GPU program cannot return actually a function result. All the data that we want to put into the function and want to get back from the function has to be passed as global memory, which we see here. The global memory is the input and the output memory, and also the length has to be passed explicitly to the function. Also, GPU functions can only take primitive types. With primitive types, maybe type ints or pointers to memory, which resides on the GPU memory. Global tells the compiler that the data arguments reside in the global memory of the GPU. The real magic here is happening in the function getGlobalID. GetGlobalID is where different threads get to work on different items, different portions of the data. GetGlobalID will return the actual index that the kernel code needs to run on, and this code will be different. This index will be different for any kernel that is kernel thread that is run by the GPU. How does the mapping of the data work here? We see this on the bottom of the slide. Important is that both the name of the kernel must match the kernel name used upon OpenCL function load, and the arguments here must match the declaration of the arguments in the OpenCL function load function. For example, here if we use integer types here, we have to use integer types here on the OpenCL function load. And finally, the third important argument are the dimensions of our block or workgroup item size. Let's look at a more complex example. This example here is so complex that I'm now using an external code which does some ray tracing. And here I'm printing the implementation of this code. Ray tracing is an interesting application which can be really easily sped up by a GPU. What ray tracing does is simply rendering a three-dimensional scene and then lets us produce a two-dimensional image from this rendered scene. And how does what ray tracing does? It traces a ray back from an observer to an object, and then computes the actual image, computes the actual pixel value that will be resulted from the projection of this 3D image onto a 2D image that makes up our pixel space. And the interesting thing about this computation that it runs the exact same computation on each pixel on the image. That means it is it's easy to run this computation in parallel because the same computation is done on each pixel. And what we are doing here, we're simply rendering a scene of spheres, where we pass spheres with a certain center and certain radii and certain color. And then we render these spheres and produce the 2D image that results from this scene. Here, for example, the kernel code simply first determines if the actual sphere actually intersects the ray that we are computing in our ray tracing algorithm. And once it finds that it intersects the sphere, we compute the color that results from tracing the ray to the surface of the sphere. And finally, we compute the color value as RGB value here and write this back as result. Here we can now simply load this OpenCL using OpenCL function load. We now use the file function to tell the OpenCL function that this source code is now provided in a file, and we can now run and load the computation. We describe the function arguments here. That means the output is given as an array. Here we pass the size of the scenery. Here we pass the data of the spheres that we are going to render, and here we have the different data, like for example the width, the height, and the color channels that we're going to use. Here we set up the actual arguments that we can use then to call the ray trace function. And you see here that here we create the spheres using some random functions with different radii and different origins of the spheres. Here we set up the centers, the radii, and the colors. And now we can, given this input, we can now call our ray trace function, and this will return the result as a pixel image. Here we see the dimensions of the result, which is 1024, and it has a depth of 3 for the different components of the color space. And we can now simply use the image function to render the image in the Mathematica session. And here you see, for example, this is the result of the it's the actual result of the rendering of the cube of the different spheres. And we can now, for example, use manipulate to create a real animation. And each in this animation, we modify the origin of the different spheres so that we can realize a scrolling effect when we move through this different, when we move the sliders of the manipulate here. And it's important to note that really every time I'm now moving a slide here, the whole Mathematica makes a complete round trip to the GPU, where it calls the ray trace function, where it copies the data to the GPU, gets the result back, and imports the result as an image, which is then shown in the manipulate here. But you see, with very few steps, we can really now realize very impressive user interfaces which run on the GPU. OpenCL also has a high-level the only high-level function which is available for OpenCL is a fractal renderer, which we can look up at now here. This fractal renderer is a complete built-in manipulate, which lets us evaluate a fractal, where we can set up the fractal parameters here, for example, in order to generate different fractal images. We can then, for example, also move the camera position. We can move the shade, and we can also rotate the resulting image. We can also move the light source here so that the shadow moves. And this is a very, and as you see, anytime I move the slide, it actually recreates the image by going to the GPU and doing the computation. Let's now move to the CUDA side of things. As I already mentioned, the machine I have is not equipped with a CUDA computable card. That's why I have pre-evaluated these functions on my office machine, which has a CUDA card. And here, everything is very similar to what we saw on the OpenCL side of things. Here, the kernel code looks very similar. We have now a function called CUDA function load instead of OpenCL load. We describe the input-output parameters and the types that are being used here. And here, one interesting thing is if I set the print option on the shell function option, we actually see what's going around behind the scenes. And here we see on the CUDA side of things, Mathematica relies on the GPU, NVIDIA GPU toolkit installed on the machine. That means in order to use NVIDIA computations from Mathematica, you have to install the NVIDIA GPU computing toolkit on the machine. This will provide the necessary NVCC compiler, and this NVCC compiler is used to translate the kernel code into machine code, which can then be run on the CPU. And another important thing is that the machine also needs to have installed a regular compiler. For example, on my desktop machine here, I have installed the Visual Studio compiler because the NVIDIA NVCC compiler also needs a regular compiler installed on the machine in order to do the computation. So setting up all things is much easier on the OpenCL side of things because you don't have to install as many drivers and additional tools which are required on the CUDA side of things. But as we see here, we can then simply call the CUDA function the same way as we did with OpenCL, and it returns the same result. If we now have a look at the differences between the OpenCL and the CUDA kernel code, we see that actually both functions are very similar. The only small details are different. For example, Here, instead of using kernel annotation, we have to use the annotation global here. And here, in OpenCL uses global for a different thing, where we don't have to use an annotation at all for the memory on the CUDA side. Then what's also different is the actual index computation is different in OpenCL and CUDA. As we already know, in OpenCL we simply have to call the get global ID function in order to get the index of the portion of the data we're going to work on. And here on the CUDA side of things, we have to do the computation of the index ourselves. And we are, and what CUDA does is we have CUDA provides us with a global thread index variable where each thread gets a different thread index, and we can then compute the global index in a similar fashion. And here, the actual computation is then done in the same way in both kernels. So it's just really minor details that are different for both styles of kernel code. That means once you have one kernel code, usually it's very simple to port one kernel code from to the other kernel code, which makes things nice and easy. What about high-level programming? CUDALink offers many high-level programming functions, like, for example, for list processing, we can use CUDA map, CUDA fold, CUDA sort, CUDA total. These work in the same way as the built-in functions map, fold, sort, and total, but they are executed on the GPU. In the same way, we have functions for image processing, like CUDA image map, CUDA image subtract, multiply, and so on. We have linear algebra functions and Fourier functions, like, for example, CUDA dot, CUDA transpose, and CUDA Fourier transform. We have functions for doing pricing of financial derivatives, like, for example, CUDA financial derivatives can be used to price options on the GPU. And another very recent addition to Mathematica are neural networks, and these neural networks can use the target device GPU upon training, which only works for NVIDIA GPU cards, because only these NVIDIA GPU cards have the built-in net train functionality. So summing up, we can say that I've now collected some resources for doing these kinds of OpenCL on CUDA programming. Here some general introductions on OpenCL programming and CUDA programming, then some references on Mathematica, where the tutorials are really very good, and they contain many of the examples that I have shown you here. And there is also an important site is also the CUDA resources site on the Wolfram site, where you can, if you're using an older version of Mathematica, you can download the correct version of the CUDA packlet, which needs to be installed on Mathematica in order to work with the existing NVIDIA device on your machine. And there's also another video which also contains an introduction to CUDA programming on the Wolfram Mathematica. To sum up, if you really want to get the best performance out of GPU programming in Mathematica, you probably want to prefer CUDA, because this is the much more efficient API, and also it lets you, the API itself lets you do some tricks that you cannot do with the OpenCL API. On the other hand, if you want to target many different devices, and if you want to write portable code which then runs on many different GPU devices, you're probably better off using OpenCL. Good. This sums up what I wanted to talk about. And are there any questions on doing GPU programming with Mathematica? Do you have any of you experience with GPU programming? Are there any other questions?